Okay, in this part of the lecture, we're going to look in detail at regression splines, which involve fitting separate low-degree polynomials over different regions of X, but the regions are going to be defined by the positions of knots. Now, otherwise known as piecewise polynomial regression, so that is what a spline is, a model of degree d with a single knot at point kappa would take this form here. So what this is of degree d, you can see here the polynomial is of degree d, but we split the model into two parts. We fit a separate polynomial at one side of kappa and a different polynomial the other side of kappa. So we're fitting two different polynomial functions to the data, one on the subset of observations where xi is less than kappa, and the other on the subset of observations where xi is greater than or equal to kappa. And you can see from what we've discussed earlier and from this expression here, each of these polynomial functions can simply be fitted by least squares. It's just a linear and parameters form. There's nothing special about it. Least squares is the best way to fit it. Just two things worth noting. If we had no knots here, then a piecewise polynomial with no knots is just a polynomial regression. It'd just be one of these expressions here, which you saw at the start of the lecture. But step functions are a piecewise polynomial regression with just the intercept term. So if we remove all of the x terms and the powers of x and just have beta 01 and beta 2, that would be a step function. So that demonstrates quite nicely how polynomials and step functions are being brought together in semi-parametric regression. Now, as we saw previously, more knots will lead to a more flexible piecewise polynomial. So if we place k knots over the range of x, then k plus 1 different polynomials of degree d are fitted. K plus 1, of course, because k knots creates k plus 1 intervals. So we're fitting a polynomial in each interval. Now, without any further conditions, the curves in each interval will be disjointed. That is, discontinuous at the knots. In other words, if we don't impose any condition on these equations, they won't connect. So we'll just have a polynomial on one and a polynomial on the other, and there'll be a discontinuity at the boundary where they don't connect. To address this issue, we have to impose constraints to ensure that the fitted curve is continuous and smooth at the knots. So we're going to impose constraints. And to improve smoothness and continuity for a piecewise degree d polynomial, all we need to do is impose continuity in derivatives up to degree d minus 1 at each knots. So we're going to do this in the following way. We're going to do it in a basis function way. We're going to define y as an expression written not in the x themselves, but in basis functions defined on the x, and we're going to use what's called a truncated power basis function. So here we have beta 1 times b1 xi up to beta d bd xi, and all these basis functions are, these ones here, are just power functions from 1 to d. So that's going to be x to the power of 1 up to x to the power of d. Then we have these basis functions k plus d, bk plus d of xi, and these are defined by these equation here. And these are going to be, these are the truncation basis functions. And what these are going to do, and we'll demonstrate it below in a concrete example that will make this very clear, they're going to ensure that the function and its derivatives either side of the knot are continuous. And rather than explain it with these abstract equations, I'll show it down below when we specify a particular basis function of, a particular degree 3 polynomial basis. So that's the first thing. We need to impose constraints in order to ensure that the functions themselves are continuous and their derivatives. The functions are continuous means that they'll connect. If the derivatives are continuous, it means they will be smooth at the points of connection. Okay, the next thing I want to talk about is degrees of freedom, because it's important. Now, fitting a separate polynomial in each of our k plus 1 regions would actually use a lot of degrees of freedom. It would use k plus 1, that's the number of intervals, times d plus 1 degrees of freedom. D plus 1 is the number of parameters in each polynomial, because of course we have an intercept. So we use k plus 1 times d plus 1 polynomials. With a degree d spline, where we've imposed constraints to ensure continuity in derivatives up to degree minus 1 at each knot, that's only going to use d plus 1 plus k degrees of freedom. So we save substantially on degrees of freedom by reducing the number of parameters. And this is because the imposition of constraints in the regression spline actually frees up 1 degree of freedom per constraint at each knot, because it reduces the complexity of the piecewise polynomial fit. And we don't have to find where the regression is going to fit at the end and start of each knot, because we're constraining it. So for instance, if we take a cubic spline is a piecewise cubic polynomial with k knots. That has d minus 1 constraints. So it has continuity of the function itself, continuity of the first derivative, and continuity of the second derivative. Sorry, it doesn't have d minus 1 constraints. It has continuity up to d minus 1. It has 3 constraints. So continuity of the function itself, continuity of the first derivative, and continuity of the second derivative. And again, I'll demonstrate this tomorrow in the next slide, or a couple of slides. I'll show you how this actually works in practice. So this cubic spline then is going to use a total of k plus 1, that's the number of intervals, times 3 plus 1 parameters, that's the number of parameters, minus the constraints, and there's 3 constraints at each knot, which is going to equal 4 plus k degrees of freedom, which is what we've said here. So d is 3 plus 1 plus k. If we had a linear spline, that's a piecewise linear polynomial with k knots, which is only continuous at each knot, so its derivatives aren't continuous, it's just the function itself that's continuous. Then that would use k plus 1 intervals times 2 parameters, beta naught plus beta 1, minus k constraints equals 2 plus k degrees of freedom. So constraining splines is useful. Not useful, it's crucial, because it connects them and it gives smoothness and it reduces degrees of freedom. So let's look at this example just to make this very concrete. We have a cubic spline here with just 2 knots, kappa 1 and kappa 2. So we write it in its basis representation. It is, as you know, a linear in parameters model where the parameters are multiplying through by the basis functions. The basis functions are written out in full here. So b1x is x itself, b2x is x to the power of 2, b3x x to the power of 3. Then we come on to the basis functions that are the truncated power basis functions. Truncation being used to impose constraints, and these are b4 xi minus the first knot cubed, that's to the degree of the polynomial, and that's important because that is going to ensure continuity of the function and its 2 derivatives. And beta 5 is going to be concerned with the second knot, again raised to the power of 3 to ensure continuity of the function and its second derivative. So just to check our degrees of freedom, this model has 6 parameters. That's the degrees of freedom we're using. It has 3 intervals, because there's only 2 knots, times 4 parameters per interval, but we've imposed 3 constraints at each knot, so we end up with 6 degrees of freedom. Now we can estimate this model by least squares, that's straightforward. Importantly, note how continuity is derived, continuity of function is derived in the model. When xi is less than kappa 1 and when xi equals kappa 1, then the basis representation is going to reduce to this equation here, because that's going to equal 0 when xi is less than kappa 1 and xi equals kappa 1. As soon as x as kappa 1 is less than xi, which is less than k2, then we have to add on this basis function here, beta 4 xi minus kappa 1 cubed. And that's going to impose continuity because those two piecewise functions are going to meet at the naught. That's how we impose continuity of the function. Continuity of the derivatives is going to be imposed because these expressions here, again, are going to meet at the denots. So the rate of change is going to meet at the naughts because of these expressions here. And the continuity of the second derivative, the change of the rate of change, is going to be given by these expressions that meet at the naughts, ensuring smoothness of the function. So we can look at this graphically at how it works. It's illustrated in the figure below, which shows a series of piecewise cubic polynomials with increasing orders of continuity. So the blue line is the function that we're trying to estimate, and the green line is what we're achieving with our cubic spline. Now in the first panel, there are no constraints have been imposed, and therefore the loose ends of our polynomials, our cubic polynomials that we fitted in each curve, don't match up. They're not continuous. They're just three polynomials with a discontinuity at the naughts. In this diagram here, we forced the polynomials to have to tie up by imposing continuity in the function, and you can see that that means we now have a nice continuous function across the naughts, but it's not particularly smooth. We've now constrained the first derivative to be continuous, and that adds smoothness because the rate of change of the function has to be equated over the naught, not just the function itself, and over here, so it's much more smooth. And then requiring that the second derivative also be continuous at the naughts produces a nice smooth function that nicely approximates the blue curve that we're trying to model. So this function in the lower right hand panel, that is the cubic spline we've discussed. It's this cubic spline here. It is continuous first and second derivatives at kappa 1 and kappa 2, and it provides a nice approximation to the cubic function that we're trying to estimate across the range of the data. Just one final point to make on this. Unfortunately, splines can have high variance at the outer range of the covariates. That is when x takes on either a very small or a very large value. And for that reason, sometimes natural splines are used. And this is a regression spline with an additional boundary constraints on top of the constraints that we impose on a regression spline. And that is the function is required to be linear at the boundary. So this just stops it getting too wiggly. So natural splines then impose two additional constraints at each boundary region. The spline function is constrained to be linear in the region where x is smaller than the smallest naught. That's the left-hand side boundary interval. And the spline function is constrained to be linear in the region where x is larger than the largest naught. That's the right-hand boundary interval. And these additional constraints generally produce more stable estimates at the boundary. That is, the corresponding confidence intervals that fit at the boundary are narrower. And I'll show an example in a minute when we fit it to the error data that demonstrates that. Before I do that, I want to talk about how we choose knots, because they're obviously very important in fitting a semi-parametric model. So a spline regression with k knots involves fitting k plus 1 polynomials, as we've seen, subject to some constraints. I also showed you earlier that the greater the number of knots, the more flexible is the fit. And this is because the created intervals or regions, in those regions, the polynomial coefficients can change rapidly. However, if we fit too many knots, we lead to overfitting. So overfitting, as I said earlier, is when rather than fit to the function that we're trying to estimate, we're fitting to noise in the data. So the natural question that arises is, where should we place the knots? Now, one option is to use evidence in the data to look at the data and say, let's place knots in three places. We'll place knots where there's an obvious distributional shift in direction, because we want to capture that nonlinearity. We'll place more knots on regions where we see more variability, and fewer knots in places where the function seems more stable. And all of that seems to make sense and could be appropriate. But in practice, actually, it's common just to place knots in a uniform fashion, again being kind of semi-parametric about it and not imposing too much a priori assumptions. And to do that, all we need to do is select the desired degrees of freedom, which is equivalent to the number of knots, because of course one is a function of the other, and place the corresponding number of knots at uniform quantiles of the data. So the question then is, that's how we can choose the location, but how many knots should we use? Or equivalently, how many degrees of freedom should our spline contain? With a small degree of freedom, we're going to have a less wiggly fit than we will with a big degree of freedom. And again, I'll show that in a minute. So one option is to try out just different numbers of knots and see which produces the best looking curve. So you just do it almost manually, so by hand, so to speak, just estimate with different numbers of knots and see which you prefer. And in certain situations, this will be a good way of doing it, because it really, rather than automating things, there's a certain amount of domain knowledge that can be used in knot selection. Another option is to automate it, to use cross-validation, and there's a review slide later in the lecture that explains what cross-validation is, as a more objective selection criteria. And essentially what we do there is we remove a proportion of the data, say 10%, and we fit a spline with a certain number of knots to the remaining 90% of the data. And then we use the spline to assess the goodness of fit for the held out proportion, for the 10% that we didn't use. We repeat this process multiple times until each observation has been left out once, and then we can put the overall cross-validated residual sum of the squares by adding together the errors from each trial. And this procedure is repeated for a different number of knots, and we simply select the value of k, the knot number that gives the smallest residual sum of squares. Okay, so let's look at regression splines in practice. We're going to fit a cubic spline with 5 knots, and to do that we load the library called splines in R. This is going to fit a regression spline for us, and we fit a model, linear model. Nox is our dependent variable and air temperature is an independent variable, and we specify here a basis function for air temperature with a pre-specified number of knots. So we've defined the knots here. The default degree of the spline in this model is cubic, but we can change that by specifying some other degree if we wanted to. As always, we're not interested in the individual coefficients, we're interested in the grid. This is estimated by least squares, of course. We're interested in how the function looks over the range of the data as a whole. So we do the same thing. We predict the function for a grid over the support of air temperature. We calculate the standard error bands to give us our 95% confidence intervals, and we simply plot the result. And this is what we get. This is a fitted cubic spline in R. We've pre-specified the knots, as I said, at certain temperature values, and this produces a spline with 8 basis functions. So that is 5 knots plus the 3 elements, 3 degrees of polynomial. So 3 plus 5 equals 8. Also recall that a cubic spline with 5 knots has 9 degrees of freedom. That is d plus 1 plus k, so that gives us 3 plus 1, 4 plus 5 is 9. And these degrees of freedom are used up by the intercept plus the 8 basis functions that appear in the cubic equation, as you saw earlier. And you can see here that the dotted lines again are the confidence intervals. The thick smooth line is the fit, and we can see that we've got a nice smooth fit from this 3rd degree cubic spline, the cubic spline here. We've got a nice fit through the data that looks nice and smooth. Now if we wanted to change things, we can use the df option to produce a spline with knots at uniform quantities of the data, and we can use the degree option to specify some degree other than cubic, and we can look at how they compare. So we can reduce the degree, we can increase the degree, and see what happens, and that's definitely something worth doing. Okay, we'll now look at using a natural spline. So we're going to use the ns function in R. This is this function here, rather than the one we had previously was bs for the regression spline. We're now going to use ns for a natural spline. So what the natural spline is going to do, of course, is it's going to fit the linear function in the boundary regions. It's going to fit, it's going to be linear in the boundary regions, as we said previously. Pre-specified uniformly spaced knots, as we did before. Exactly the same process. We generate the GID, we calculate the confidence interval, and we plot the results. And the results are shown here. And of course, it looks very, very similar to what we got from the regression spline. Worth noticing here that compared to that flitted regression spline model, the knots that we have with knots at the same location, the confidence intervals at the boundary are narrower. So that indicates that actually the natural spline is doing the job that we intend it to do. It's addressing high variance in the boundary intervals by specifying that as simply a linear function at those points and not allowing it to be too wiggly.